Namaste. Hope you are doing well. Today we will solve the 25th question of ISI MSTAT 2024 PSA. And yes, it's a regression question or a least squares theory related question. Whether you are given two modeling setups, both have the same dependent variable set, but in the first one you are using only one independent variable to predict. This is the associated coefficient estimate, and in the second you are using two independent variables to predict. These are the associated coefficient estimates. And you are given four options and you have to evaluate which one is correct, wherein all the options involve the error sum of squares or some structure like error sum of squares. This is the error sum of squares for the first model. This is for the second model, and they two are repeated in some options. This is basically error sum of squares in the second model, but we are not counting the contribution of x. We have already computed the coefficients for y and x using both y and x, but while calculating the error sum of squares, we are only using y. And similarly, in this case, we are only using x. So these are the options. Let's get started. Now, connecting some dots. Because it's an MCQ, can we eliminate some options? And looking at options A and B, we find an interesting thing. Because option A is saying that the error sum of squares for the first model is greater than or equal to that of the second model. The option B is saying the exact reverse of that. That is less than. Now, if option A is correct, anyway all options are wrong, that's fine. But if option A is incorrect, then it means the exact opposite of it has to be correct. That's how logic works. So in either of the cases, option A or option B, the right answer has to be from both of them. And the second thing that we have to connect is least squares theory is a big chunk. What can be useful over here in this context? And because we have so many error sum of squares, the part that could be useful is the minimization of error sum of squares in the theory of least squares. And let's see how it helps us in visualizing certain things and getting to the answer. Now, what least squares does is minimizes the error sum of squares for the given model. Here we have the first model with only one independent variable. Essentially, the setup is going to have the error sum of squares are going to have an associated space where all sorts of values for this beta x can be there, and choosing from that space, we choose that value that minimizes the error sum of squares. That's the setup. Interestingly, this space is actually a subset of a bigger space of optimization in which you are considering a bigger model with an additional variable added. And the way to see that is, if you choose in this bigger space, in this bigger circle of values, there is a possibility of having the coefficient for y as 0. And the moment you do that, this thing vanishes from the setup, and what you are ending up having coincides exactly with the first model. The notation may be different, but they are telling the same. And this is why we see that the set of possible solutions considered for the coefficient of x in the first model are a subset of those in the second model. And that's why the answer is option A. And it's quite intuitive as well, that you add more information in the form of predictor to the model, and you would end up having more power, predictive power, and hence less error. That very well encapsulates this. And then there's this optimization theory angle as well. And some ways to build your base is the journey of 1,000 miles already has one step. So you don't have to think about one step. And this connection here is with this optimization problem, wherein this bigger problem having two variables already sort of takes into space the solutions coming from the first model with only one variable, but the variable has to be common. And that's it. If you like this video, then do share one such scenario where your initial objective was to optimize a smaller problem in your life, but you ended up thankfully optimizing a bigger problem. And take care. Hare Krishna.